Okay, I can see we have almost 100 people connected. Okay, so I think we are all here, so let's start. Welcome, everyone. I'm Véronica Royot from Itasca, France. Thank you for taking time out and being here today for the webinar Applications of Python in Itasca Codes. Our today's presenter is Dr. Huy Tran. Huy is a geotechnical engineer and software developer. He has worked on various consulting projects and he is now involved in the development of Itasca software, FLAC 3D and 3DEC. So if you have questions during the presentation, please type them into the question box in your GoToWebinar control panel on the right-hand side of your screen. I'll bring them up at the end of the webinar. And if you miss anything, the recording will be available on our website in a couple of days. So can we start now?
Okay, thank you, Vigolik. Hello, everyone. So so my talk today is about Python in Itasca software. Okay, yeah, it's it's outline of my talk today. I will start by covering what a variable within Itasca software for Python, and then I will show how we can run and write the Python script in Itasca software, and what we can do with the Itasca model. And I will show you what's the difference between Fish and Python. And finally, I will show you some example. Okay, so Python is a variable inside BFC, FLAC3D, and 3DEC. Is the Python version 3 in the last versions of Itasca software. So as you know, we in Itasca software, we have a built-in programming language called Fish. So why we need Python? So the Python is very popular programming language. It's easy to use and learn, and Python is so fast. It can see here on the table. On the table, we just did some comparison in terms of the speed between Fish and Python for some common obligation. For example, we do a loop over the zone list here or the grid point list. And so you can see that Python is extremely fast, especially with the NumPy. And okay, so I think the main reason why we want to use Python is to have some additional feature. So we can do basically everything from do some optimization or interpolation with SciPy, for example, or we do some advanced visualizations with Matplotlib, or even to create the user interface with PySci. And it's out the webinar today, and which give you at the end of the webinar some idea to attend the capability of the Itasca software with Python. Okay, so the basic way to interact with Python within Itasca software is through IPython console here. So basically, to open it, you can go to menu here, IPython pop-up, and choose IPython console here. So it's actually a Python idle where you can write and test the Python script, but it doesn't allow you to save a Python script into the memory itself. And to actually write and run the Python script, you can use the Python editor here. Here on the right, we have a Fish editor. And on the left here, we have a Python's editor. So basically, but the Python editor is exactly the same as the fish editor. The only difference is for the Python script, you need to save as .py file, and the these two scripts basically do the same thing. It's just print out to the console here, the, just hello world. And the only difference is for the fish script, it's just print out to the Itasca console. But for the Python script, the output is through the IPython console. I can see here. Okay, so the Itasca module is the main package which provides connectivity to the Itasca software. And this Python package contain the class which represent the different type of the Itasca software, such as the zone, the block, the grid point, and so on. It contains also the different function. For example, you can get the number of zone, find the different object, for example. So for most of each function, you can find the equivalent Python function in this model. And basically, if you want to use this model in the Python script, you just import Itasca, you can see here. And so we can use the Itasca model to call the Itasca command from the Python to get and set the fit variable from the Python, and also call the fit function during the cycling sequence. And we can also detach Python state from the model state. What do I mean by that? So as you know, in with fish, when a command model new or model destroys, it gives the fish variables will be clear. But for the Python variable is not reset if you just set the Python reset state if to 4. And by default, the Python variable is not saved in the save file, but you can save the whole state, so whole Python state, or only certain variable if you want. So this feature is allow Python to be higher power. So you can basically execute the function, but the Python function independent of the model state. And so it's very useful when, for example, you want to do a parametric study, or you want to do some optimization with SciPy, for example. So we will go to see that in the following example. And here I want to show you some 4 or 5 example with Python. So the first example here is I want to simulate the initial compression strength of a jointed material, and then I want to see the effects of the orientation of the wedge plane. So the basic curve of the UCS over with the wedge plane orientation you can see here. For this example, you can find in the Flux 3D documentation. You go to have example, and you can find this example in the verification problem. So I'll show you on. Oh, sorry. So show you here in the with the Flux 3D here. Okay, so here is an example with for the jointed material. So when you open here, for example, if I can do that with fish, that means here I can run this simulation. So basically, with the different value of beta here is with plane orientations. I can do it. I can do that with fish. That means every time I need to modify the value of beta here, but well, I can do better with fish. So basically, I just comment this 9 here and this nice, and I move it to these two line to the Python script here. Okay, so basically here I should comment these lines, and okay, so basically here for the Python script, I want to study the effects of the width-band orientation every 5 degrees from 0 and 90, and I do have a loop over this list, and each time I just call the function or call the model new, change the value of beta, and call the fish script. So now I just run the simulation. As you can see here, here we are solving the problem with the width-band orientation of 0 here. And okay, so next time is fine, and so on. So so it's very simple. And now when we finish, when we finish the simulation, I just want to plot the curve of UCS over the with the weak plan orientation. For example, I just stop here. Okay, so I just comment here, and I just run here. I will use matplotlib to plot the curve of the UCS here. And here I have an empty place for the UCS, and every time I can rechoice the Z file, and I can calculate the compression strength with this function here, and I can plot this curve. Then let me run this this script. Okay, so finally here's the result. You can see, oh, it's pretty small here, but you can see that here is the curve which represent the variations of the compression strength with the width-band orientation. So it's pretty simple. Okay, let's come back to the presentation here. Okay, the next example is a very common situation where I want to initialize the paw pressure from the data set. So basically, I have some data sets that you can see here, and the problem is the positions of the points cloud here is not exactly the same as the positions of the mass of the grid point in my model. So to set the paw pressure in my model, I need to do an interpolation. So how I can do that? It's quite simple. So I can use a function in SciPy. It's to interpolate the values of the paw pressure here. And okay, and go back to Python here. Go back to Flux 3D here. Okay, it's my model here. You can see here we don't have any the paw pressure is not set in my model here. So basically here I will use the LAMPy to read the data set here, and then I will use the function, this function get data from the SciPy package here to just interpolate the paw pressure value, and I use the function in the Itasca model to set the paw pressure here. So I should run it. Okay, so you can see here the paw pressure is set in my model, and with only 3 or 5 line of code here. And okay, so next example here is here for the next example, I want to simulate a tunnel excavated in a hot brown medium, and here I have some measurements, some displacement measurement inside the rope master with the extents semester, for example. And here is the famous Hopf-Brown criterion, which define with a different parameter. So the question is here, I want to calibrate the property of the Hopf-Brown criterion from the extensomet measurements. So how can do that? We know that we can estimate the values of the different parameter of the Hopf-Brown criterion from the GSI index. So okay, here is you can see here is the data from the extensomet. So if I go back to wow, I go back to Flag 3D here. No, it's not that, sorry. And here, yeah. So basically, what I can do is just I can use the the function f bar in the SciPy to optimize the value of this set. So I use this function f function bar. Basically, it will call the reduce your function. In this function, I will try with the different value of GCS, and in this function, which will call the function to compute the displacement inside the rope mass. And within this function, basically, I just every time I just update the property of the rope mass with this SI value, and finally, it will return the values of the displacement inside the rope mass. And finally, I will plot the curve of the displacement with the distance from the tunnel, and this function will return the difference between the data and the numerical value. I should run it here. Okay, so okay, wow, it's quite small. Okay, I can see here I'm testing with the trial value is this chest is about 40 here. Well, yeah. So you could try the different value. Now I try with the different value here, and after X iteration, you can see here the numerical result will get closer to the data data set you can see here. And well, at the end, with this function, I can get the optimal value of this set. So, okay, so it's quite simple here. And okay, so for the example, and go back to the presentation here. Yeah, for this example, I just want to show how we can create some small application with Python within Itasca software. So here I want to create a small application to simulate the tunnel excavation, taking into account the different shape of the tunnel cross section. And okay, so I go back to Block 3D here. Wow, yeah, okay, yeah. Oh, where is my? Sorry, I can open my Python script here. Oh, it takes time. Wow, what happened? Sorry. Basically here with this application, I can change, I can modify the dimensions. I can choose a different type of the cross section, and then I can, okay, so show you here. I can change the dimensions of the cross section, and then I can choose the typical size and ratio for the maze. Well, I go into detail about the Python script here. To do that, I just use PySide. PySide actually is Python binding for the Qt platform. And here I need to create some window. I create some different bottom and the edit box. And I need also connect, for example, here connect the different button with different function here. For example, this function to create the mesh. So basically, this function will call the Itasca command to create the mesh. So we go back here, and for example, if I can choose a different section shape here, for example. Wow, I can press here. You can see, and here, for example, well, I can choose a cross section, for example, and then I can apply the property, assign the property for the drop mass, for example, and assign the property here, and then I can also initialize the trace in the drop mass here, and yeah, so and then I can run the simulation, and wow, I can see here. We can see the contour of the displacements around the tunnel. Wow, yeah. And okay, so come back to the presentation. Okay, here is it. It's very nice emission, but this time with PFC. Okay, so I also use BiSide to create example. Here I want to simulate the rotating drum here. And okay, so here I can, for example, choose the different geometry for rotating drum here, and can set the speed and the number of revolution, for example, and then I can choose I can set the mechanical and thermal parameter for my motor. And okay, and I run here, and here for this example, the temperature is on the run here is set to 1000. So now we can see how the temperature can be propagate inside the drum here. So okay, so I think is my last example. Well, I come back to simulation, so presentation here. Okay, so it's my last example. If you know more about Python in Itasca software, we have some Chinese class, and I should let my colleague, talk more about that.
Thank you, Wee. Yes, thank you for your attention too. So yes, I just wanted to bring your attention to some upcoming events. So we are going to give a FLAG 3D online training course in May. Registrations are already open if you are interested. There is also an upcoming Python training course in June. It will be organized by Itasca France, and it will be a half-a-day training course. So if you are interested by this event, you can check regularly our website, and we will post information on the section training. And at last, the FLAG 2D pre-release will be available in 2022, this year, and you can already pre-purchase the new version and make savings. So I invite you to contact us at software@itasca.fr for more information on these events. Okay, so I thank you all for your attention. Thank you, Wee, for this presentation. And thank you again for joining us today for this live webinar. And we will see you next time. Thank you all. Bye-bye.
Thank you.